Having already introduced the notion of a complete residue system, now we move on to what are called reduced residue systems. So remember that a complete residue system modulo n is a choice of one element from each equivalence class under the congruent modulo n equivalence relation. A refinement of this idea is what's called a reduced residue system, but first we're going to make an observation. First, if A is equivalent to B modulo n, then the greatest common factor of A and n is the same integer as the greatest common factor of B and n. The proof is fairly direct, so if A is equivalent to B modulo n, then A is a multiple of n plus B. So anything that's a common factor of A and n must be a common factor of a linear combination of them, specifically A minus nk, which is exactly B. So any common factor of A and n must also be a factor of B, and similarly, any common factor of B and n must also be a factor of A. So anything that's a common factor of A and n is also a common factor of B and n, and vice versa. So since the set of common factors is the same, their greatest element is also the same. However, this is not true in the converse. It's definitely possible, and in fact not very difficult, to find examples of integers so that the greatest common factor of A and n is the same as the greatest common factor of B and n, but where A and B are not equivalent modulo n. For example, 1 and 3 are both relatively prime to 4, but 1 is not equivalent to 3 modulo 4. As a corollary, if we were to fix n, at least as large as 1, every element of a given equivalence class modulo n will have the same greatest common divisor with n. Because they're all equivalent modulo n, they all have the same greatest common divisor. So what we're going to do is we're going to label equivalence classes with whatever that greatest common divisor is. And the cautionary statement above tells us that two different equivalence classes might end up with the same label. So suppose capital S1 through capital Sn are the equivalence classes under the mod n relation. Recall that the division algorithm does guarantee there are exactly n such equivalence classes once the positive integer n has been chosen for the mod n relation. So we're going to make a set capital S formed with elements little s1 through little sk, and observe this counts up to k, which may or may not be the same number as n. And here are the conditions I place on my set capital S. First, just as in the case of a complete residue system, for each equivalence class, at most, one element is drawn from it. If the equivalence class consists of things which are all relatively prime to n, then you do have to pick one such element. And conversely, every element you pick must be from an equivalence class of relatively prime elements to n. So what you have done is from each equivalence class, you've labeled it with whatever the greatest common factor of those elements and n would be. And if that equivalence class consists of relatively prime elements to n, then you do in fact pick something. So instead of picking one element from every equivalence class, that's the complete residue system. For a reduced residue system mod n, you simply pick one element from each equivalence class that is stuff relatively prime to n. And we're going to call these reduced residue systems mod n, or just RRS mod n. Now the division algorithm made a very transparent choice of a standard complete residue system mod n, just the possible remainders 0 through n minus 1. We're going to do some similar steps for reduced residue systems. So the equivalence classes can be pretty easily labeled with what the division algorithm spits out as the remainder, 0 through n minus 1, and this is how we made the standard complete residue system mod n. To form a standard reduced residue system mod n, we're only going to take the ones that are relatively prime to n, because recall, a reduced residue system has one element from each equivalence class which is relatively prime to n. So from the standard representatives of the equivalence classes, we just keep the ones relatively prime to n. So for example, can we construct the standard reduced residue system modulo 10? Well, the standard complete residue system mod 10 is just 0 through 9. And now what we're going to do is throw out the ones that are not relatively prime to 10 and keep the ones that are. So if we remove the things that fail to be relatively prime to 10, 0, 2, 4, 5, 6, and 8, What's left behind is just 1, 3, 7, 9. And here we have the standard reduced residue system mod 10. We started with the complete residue system, the standard complete residue system, and we only keep things relatively prime to the base. Note, however, this is not a complete residue system mod 10. It doesn't have 10 elements. It's not a complete residue system. This is something different. Another example, construct the standard reduced residue system modulo 30. So again, we start with the list 0 through 29, the standard complete residue system, and we only keep the ones relatively prime to 30, and you can really just go through it. 0 is not relatively prime to 30, but 1 is. 2 is not, 3 is not, 4 is not, 5 is not, 6 is not, but 7 is, and so forth. And you would find the standard reduced residue system mod 30 is 1, 7, 11, 13, 17, 19, 23, and 29. Just as we did with complete residue systems, we can describe reduced residue systems in a couple equivalent ways. So first, we could say a set is a reduced residue system mod n according to the definition we've introduced. It's a set that has one element from each equivalence class mod n that's relatively prime to n. Second, we could say the set S has this property. Any integer relatively prime to n is equivalent mod n to exactly one element of S, and any integer that is not relatively prime to n is not equivalent to anything in the set S. Third, S has exactly phi of n elements where there is the Euler-Totient function. All are relatively prime to n, and no two are equivalent mod n. So all three of these statements here imply one another. If you have one, you have the other two. Well, the first two are really just a matter of rephrasing. Okay, so the first definition was, from all the equivalence classes, look what the GCD is. If the GCD of everything in that equivalence class with n is 1, pick one element out of it. The second says everything relatively prime to n must be equivalent to one element of S. In other words, if x belongs to an equivalence class of things relatively prime to n, then you must have picked one element out of that equivalence class. But if x is not relatively prime to n, then it is not equivalent to anything in S. In other words, if x belongs to an equivalence class of elements not relatively prime to n, then you didn't pick anything out of that equivalence class. So these first two are really just the same thing. For the third, it falls out quite quickly that a reduced residue system mod n must have exactly phi of n elements. From the division algorithm, we saw that the n equivalence classes mod n can be represented as 0 through n minus 1. And the totient function was defined to be of the things in this list, how many of them are relatively prime to n. In other words, pick one out for each element that's relatively prime to n, just count them up. So phi of n counts how many residue classes are relatively prime to n. It tells you exactly how many elements need to be in a reduced residue system mod n. And a reduced residue system can't have two elements that are equivalent to each other mod n, because by definition we took one element from each equivalence class. So you can have at most one element from each equivalence class. And by the pigeonhole principle, if there are exactly phi of n equivalence classes relatively prime to n, and we have phi of n elements with no two equivalent mod n, then you must have had exactly one representative from each such equivalence class. So this third condition is how we will typically work with reduced residue systems. Does it have the correct quantity of elements, which is no longer n, but now phi of n? Are they all relatively prime to n, and are no two of them equivalent mod n? Well, here's a theorem about reduced residue systems. It's going to look somewhat familiar. Suppose A1 through A phi of n is a reduced residue system mod n. Observe, a reduced residue system mod n must have exactly phi of n elements, so I've labeled them A sub 1 through A sub phi of n to count out exactly that many. Now let k be an integer which is relatively prime to n. Then I can form a new set by multiplying every element of the reduced residue system by the same number k, which was relatively prime to n. This is also a reduced residue system mod n. Well, we definitely have phi of n elements, so what we need to do is verify they are all relatively prime to n, and no two of them are congruent to each other mod n. The first is pretty quick. The original set was assumed to be a reduced residue system mod n. Therefore, everything in the original set is relatively prime to n. Our assumption was that k is relatively prime to n, but if n is relatively prime to two numbers, it's relatively prime to the product, from a very old result about greatest common factors. Therefore, every element in our new set must be relatively prime to n. However, let's suppose two of them are equivalent to one another. Well, if I assume these two elements from my new set are equivalent mod n, notice I have a shared factor of k here. But k is relatively prime to the base, so I can cancel it no problem, from which I will extract that the original elements ai and aj were equivalent mod n, but that doesn't happen because the original set was a reduced residue system. No two elements were equivalent. And this is very similar to a result we had about complete residue systems. If you had a complete residue system mod n and a number k that was relatively prime to the base, you could multiply everything in the complete residue system by k and still be a complete residue system mod n, and the proof was very similar. However, there was a result about complete residue systems that you can add the same number to every element of a complete residue system and remain a complete residue system. The same result does not hold for reduced residue systems mod n. Adding things very much changes what is or isn't a factor of the resulting sum, and therefore can very easily change whether something is relatively prime to n or not. So for example, 1 and 3 is the standard reduced residue system mod 4. Consider the standard complete residue system 0, 1, 2, 3. Remove the things that are not relatively prime to 4, specifically 0 and 2, and you're left with 1 and 3. So 1, 3 is a reduced residue system mod 4. 1 is definitely relatively prime to 4, but if you were to add it to every element of the set, you would get 2, 4, and those are not relatively prime to 4 anymore, so they're definitely not a reduced residue system. So you can multiply a reduced residue system by something relatively prime to the base, exactly analogously to how we did with complete residue systems, but you can't expect to add or subtract elements to a reduced residue system and remain a reduced residue system. All right, so let's start taking a look at some examples. Can we construct a reduced residue system mod 9 entirely made of even integers? We might start with the standard reduced residue system mod 9. List out 0 through 8, remove elements that have a common factor with 9, so specifically we've removed 0, 3, and 6. However, a few odd numbers remain, so we haven't finished the problem. We can't just get rid of those odd numbers, because phi of 9 is 6, so a reduced residue system mod 9 has to have 6 elements. So if we just strike out 1, 5, and 7, we would only have 3 numbers left. We also can't just replace 1, 5, and 7 with randomly chosen even numbers, because reduced residue systems have some specific requirements. Everything has to be relatively prime to 9, and no two of them can be congruent mod 9 to one another. So how can we get around this issue? Since 9 is equivalent to 0 mod 9, adding or subtracting 9 to an element does not change which equivalence class it was drawn from. If x will always be equivalent to x plus 9 or x minus 9 modulo 9, since 9 is the same thing as 0. So if we start with an odd element and we add 9, it will now be even. So replace 1 with 1 plus 9 is 10, replace 5 with 5 plus 9 is 14, and replace 7 with 16. We haven't actually changed which equivalence classes we've drawn elements from. 1 is equivalent to 10, so I still have one element from that equivalence class, and so forth. So now we have a collection of 6 elements. They are all relatively prime to 9, and no two are equivalent mod 9 to one another. Another way we could solve this is, since 2 is in fact relatively prime to 9, you can just multiply everything in the standard reduced residue system mod 9 by 2. And if I start with the standard reduced residue system mod 9, 1, 2, 4, 5, 7, 8, and multiply everything by 2, we actually get the same set, 2, 4, 8, 10, 14, 16. So 2 different ways to end up at the same place. There are many other solutions. We could add 9 many times, or subtract 9 and have some negative numbers, all of which would be other ways to change odd elements into even ones. Another example, let's construct a reduced residue system mod 13 that has exactly 4 positive even integers and 8 negative odd ones. An odd, collection of requirements, but let's go with it. So start out by writing out the standard reduced residue system mod 13. 0 through 12, remove things that have a common factor with 13. Well, you're only going to remove 0 because 13 is prime. So now we have 12 positive numbers, and they're not all even or all odd. So we're going to add or subtract 13, because 13 is equivalent to 0, to each element. For the sake of argument, let's just keep the first 4 representatives positive. So we're going to add 13 until we get even numbers. And the last 8 we'll make negative, so we'll subtract 13 until we get odd ones. So one by one, 1 is positive, but it is not even, so I'm going to add 13 to it and get 14. 2 is already positive and even. 3 is positive, but not even, so I'm going to add 13 and end up with 16. 4 is already positive and even, so I've already got my 4 positive even integers. And note, they correspond exactly to the residue system, to the residue classes. 1 is equivalent to 14, 2 was already picked, 3 is equivalent to 16, and 4 is just saying the same. So I kept these 4 equivalence classes and replaced them with positive even integers that are equivalent to mod 13. So we're just going to keep going like that, except now we're looking for negative odd integers. 5 is odd, but it's not negative. If I just multiplied it by -1, I would have a different equivalence class. But if I subtract 13, it's the same equivalence class. Unfortunately, while it is now negative, it is even. But if I subtract 13 again, I now have something equivalent to 5 modulo 13, but a negative odd number. 6, I just take away 13 and I end up at -7. 7, I'm going to have to take away 13 twice. 7 minus 13 would be negative, but it's -6, which is even. So I take away 13 again, and I end up at -19. 8, I only have to take away 13 once. 9, I'm going to have to do it twice. 10, I'm only going to have to do it once. 11, I'm going to have to do it twice. And 12, I only have to do it once. So there we have it. 14 is equivalent to 1 mod 13, 2, equivalent to 3, 4, equivalent to 5, equivalent to 6, equivalent to 7, equivalent to 8, equivalent to 9, equivalent to 10, equivalent to 11, and equivalent to 12. So it was a little tedious, but we simply changed the elements of the standard reduced residue system one by one to make sure we got 4 positive even numbers and 8 negative odd ones. So there we have it. Another example, can we construct a reduced residue system modulo 8 entirely made of prime numbers? Again, the standard reduced residue system is a good place to start. So begin with 0 through 7 and throw out anything that has a common factor with 8, so you're throwing out all the even numbers. So 1, 3, 5, 7. There's our standard reduced residue system mod 8. Of course, these are not all prime numbers. Well, most of them are, in fact, prime, 3, 5, and 7. So the only thing we can really try is to add or subtract 8 until we get a prime. We're not going to subtract it because primes have to be positive. Well, if I add 8 to 1, I get 9. 9 is equivalent to 1, so that's good, but it's definitely not prime. But if I add 8 again, I get 17. 17 is equivalent to 1 modulo 8, and it is prime. So here we have a reduced residue system modulo 8 consisting entirely of primes. Note, however, it's totally impossible to make a complete residue system mod 8 entirely made of primes. There is no prime, for example, that's equivalent to 4 modulo 8, because if it's equivalent to 4 modulo 8, it would be a multiple of 8 plus 4, which means a 4 can be factored out of it, and there's definitely no prime divisible by 4. So we would never be able to make a complete residue system mod 8 consisting entirely of primes, but we were able to do it with a reduced residue system. Can this be generalized in any way? Yes. Let n be bigger than or equal to 1. Then there is a complete residue system mod n consisting entirely of primes if and only if n itself is prime. So I can make, for example, a complete residue system mod 7 entirely made of primes. However, I couldn't make a complete residue system mod 10 made entirely of primes, because 10 itself is not prime. But there is always a reduced residue system mod n entirely made of primes. For any number n, it doesn't matter. Both statements follow from what's known as Dirichlet's theorem. If n and k are relatively prime, then there are primes p, in fact infinitely many, so that p is equivalent to k modulo n. So from this theorem, you can prove both of the statements in our theorem. So not only are there some primes equivalent to k mod n, assuming n and k were relatively prime, there are in fact infinitely many of them. So let's prove it. Just kidding, it's a very difficult thing to prove, and it uses many, many tools that we do not have at our disposal. So we are absolutely not going to touch a proof of Dirichlet's theorem.